you for the introduction. So, in motor control, perturbations are ubiquitous, and motor skills acquired over the course of time must be continuously adapted to the current conditions. Nevertheless, most of those changes are only transient, so it's really crucial to maintain stable memories that can be recovered as soon as the perturbation is gone. And this highlights a trade-off between adaptability and stability of motor representations. In the mammalian brain, two major regions involved in motor learning are the motor cortex and the cerebellum. With its recurrent connectivity, the motor cortex is able to store stable dynamics that represent a basis of motor commands. On the other side, the cerebellum relies on its feed-forward structure to generate precise responses for adapting to perturbations. Another key difference between those two regions concerns learning mechanism. With the cerebellum, that mainly relies on fast supervised learning, and the motor cortex that rather opt for forms of unsupervised learning that are slower and timescales. So this clear dichotomy is at the basis of theories concerning the interaction between those two regions during learning in general, that is partly supported by extended bidirectional connectivity between the two. Still, it remains unclear how those two regions can interact over learning. In order to address this question, it is first important to understand how neural populations can deal with transient changes. So if we take a simple recurrent network as an example, and we assume this was trained to generate a certain target output dynamics, in the case of change, of a change of the task, through synaptic plasticity, the representation of the task has to adjust. And as soon as this change is gone, the task will have to be readjusted again. And this highlights how using a single module for doing motor adaptation with variability in the environment causes continual modification of the representations and open the way to forgetting. So an easy way to solve this issue is instead to add a secondary module, keeping the memory network fixed. In this second hypothesis, the secondary module fully deals with changes and by generating the residuals from the baseline provided by the initial network. This allows to immediately restore the initial condition as soon as the perturbation is gone, solving the forgetting issue. Still, this hypothesis totally neglects how those memories can be updated over time and even learned from the beginning. We need to understand how after making the adaptation happening, how can we consolidate those memories? Available theories of consolidation in distributed systems usually relies on two stages strategies, where consolidation happens only after adaptation. While instead, in motor adaptation, learning appears to be composed as two different processes happening at different timescales, where we have a fast process that generates transient responses for rapid adaptation, and a slow process that maintains the baseline. This strategy easily maps with our network, following basically the colors. And it is our opinion that this could describe what happens between the cerebellum and cortex, that, in our opinion, follows represent a distributed two-timescale learning system. This requires a tight coordination between those two areas that, in a neural network model, we achieve the following three main steps. First, we model the motor cortex as a recurrent neural network able to perform online correction using its own error feedback. Fellner and colleagues have shown how the RNNs trained on the baseline center at reaching tasks are able to correct their own outputs in the case of like visomotor rotations without any further training. Here we train the network in order to control a simplified version of a motor arm. And as you can note here, the correction happens through the error feedback computed at the motor command level. Although this solution works for generating the correction, here we have a strong assumption, as this specific setup requires the availability of the reference of the reference of the updated motor command. This is a clear limitation. So the next step is to replace the exact error with an approximation of it that it can be computed by the cerebellum. Importantly, the same quantity can be also used to directly correct the motor command. And this solution improve convergence and also simplify credit assignment thanks to the direct pathway through to the behavioral output. Finally, on this structure, we add slow consolidation in the motor cortex in order to have to get the update of the representations. Importantly, the presence of the feedback projection to the motor cortex allows also to use a local rule in order to implement consolidation, where recurrent updates are proportional to the presynaptic recurrent neuron activity and the feedback from the cerebellar output. So this completes our model that basically shows the evolution of a two-timescale learning system as we wanted. Something that, like, in order to better understand what like the properties of our system, we evaluated its performance in a washout task, where we measure the convergence time in the second phase after perturbations of increasing lengths. So what we observe is that compared to a single RNN model, the distributed learning model shows way faster convergence for short perturbations and slower ones for very long perturbations. And interestingly, if we variate the consolidation rate in the network, what we get is that the faster the consolidation rate, the more the performance get closer to the RNN performance. The property of of the faster relearning of the model is directly linked with its ability to retain information, and this can be more directly assessed by testing the network on a series of perturbations and looking at the amount of changes in the recurrent layer. What we observe is that the amount of changes in the recurrent layer are drastically decreasing although the performance, even though I'm not showing the plot, are basically the same. Suggesting how, again, splitting the learning problem between adaptation and memorization can be can help for continual learning applications. So to summarize, we proposed this 2 timescale distributed learning model for model adaptation, where simultaneous low and fast adaptive processes are implemented in different regions, and in particular cortex and cerebellum. And where we have our cerebellum that provides an approximation of the internal error necessary to the cortex for cortical consolidation. You can find more details in our preprint, and with that I would like to thank my lab, and in particular my supervisor, and all the organizers for the opportunity. Thank you.